Hello everyone, my name is Apurv Mohan and I'm a PhD student at Northeastern University. In this talk, I will present a journal purpose approach for non-intrusive software introspection which can be used for both bare metal as well as virtual instances. This work is a result of a collaboration between Northeastern University, Boston University, IBM TJ Watson Research Center and State Street Corporation. So without any further delay, let's begin. In today's world, most enterprises are dependent on computing. And as this trend of computing driven enterprises grows further, the security of computing infrastructure becomes ever so more important for organizations. So, when it comes to the security of infrastructure driving these enterprises, organizations want to cover every possible loose end that may lead to any potential revenue loss. One of the most crucial aspects of infrastructure security is to ensure that software driving the infrastructure is not compromised. Having said that, given the constantly evolving nature of software, it can never be bug-free. Addition of new features and fixing previously detected bugs is constantly introducing new vulnerabilities in the deployed software stack. Hence, it is important that the deployed software stack is constantly and proactively scanned for software bugs and misconfigurations. The tech community has realized this aspect of software security and has developed solutions to perform continuous introspection and identify vulnerabilities that may be exploited by malicious entities to cause damage. The state of the art of such solutions implement agent-based approaches to introspect the provisioned software stack. A security agent runs on every instance just like any other application while analyzing the instance for vulnerabilities. IaaS cloud providers such as Amazon even offer deployable agent-based introspection solutions and pre-baked images with such security agents. These agents periodically scan the file system and compares its findings against a database of common vulnerabilities and reports its finding to a centralized monitoring system. However, using agent-based approach for software introspection has several shortcomings. First, security agents themselves may become vulnerable and lead to new attack vectors, as they may be hijacked by co-located malicious programs. Next, while performing introspection, these agents consume system resources such as CPU, memory, or network, which can impact the performance of the primary workloads. To understand this, we analyze the performance impact on the running workloads due to co-location of different introspection techniques. As the introspection techniques competed for resources with the workloads, we observed a performance degradation of up to 12% with different class of applications. In a public cloud setting, such a performance degradation can lead to violation of SLAs. However, if organizations were to reserve resources for such agents on every machine to avoid performance degradation, it could lead to resource inefficiency. For example, in a cluster of 10,000 machines, an organization would have to reserve up to 1,200 server worth resources in order to tolerate any performance overhead that could potentially be caused due to co-locating security agents. Furthermore, as an agent is required to be installed separately on every system, the operation and maintenance of such agents become challenging at cloud scale. For example, introspecting 10,000 bare metal instances would require deploying and managing the same number of agents. And moreover, the security agents are infamous to cause network congestion if sufficient network resources are not reserved for them. Over the past decades, many efforts have been made to overcome the shortcomings of agent-based introspection. However, they have several issues. First, there does not exist a single non-intrusive software introspection solution that works for both bare metal as well as virtual instances. Next, the non-intrusive solutions available for bare metal do not work with commodity hardware. Further, the non-intrusive solutions available for virtual instances by public cloud vendors are implemented at the hypervisor layer and are subjected to performance degradation or resource inefficiency problems presented in the previous slides. On top of that, today's public cloud vendors provide one-size-fits-all solutions for all its tenants, where the tenants have limited visibility and control on different security implementations, which is not acceptable by many security sensitive organizations who refrain from using public clouds. So with these issues at hand, we ask ourselves, is it even possible to design a software introspection system which is non-intrusive, general purpose, and tenant controllable at the same time? As we searched for the answer to this question, we identified that the primary requirement for such a system is to have continuous and non-intrusive access to the current software stack state. So the next question is, how do we get such an access? Using disaggregated storage helps in getting continuous and non-intrusive access to the current state of the software stack. It provides a clean separation of the provisioned software stack from the running instance, as the instances can be provisioned to a virtual disk residing on a remote distributed storage. Furthermore, modern distributed storage solutions enable creation of lightweight read-only snapshot for block devices, which can be exploited by different introspection APIs. Such a disaggregation enables a simple and practical mechanism for non-intrusive access to the state of the provisioned software stack. It eliminates the shortcomings of agent-based approaches, as running a security agent on every provision instance is no longer required. Furthermore, this approach of disaggregating the instance from its persistent state can be applied to both virtual as well as bare metal instances. Which brings us to the third part, that is tenant controllability. To address it, we designed our system to be a set of microservices which can be deployed by security sensitive tenants with minimal intervention from the provider. We identify four microservices that are required for non-intrusive software introspection. The first microservice is responsible for provisioning of instances. It enables diskless provisioning of virtual or bare metal instances. That is, the instance boot from a desired software stack from an image residing on a remote storage. Next is the image management service. It is responsible for hosting remote mounted images for provisioned instances. It also provides APIs to rapidly snapshot or clone a provisioned instance's image. Next is the introspection service. It is responsible for scanning the latest available snapshot for software vulnerabilities and misconfigurations. It maintains a database of known vulnerabilities which is updated by querying a publicly available vulnerability database. For security sensitive tenants, this service should also have a mechanism to manage encryption keys to be used when mounting encrypted disks. Last is the orchestration service. It controls the non-intrusive introspection workflow among the other microservices. It provides an interface to submit introspection requests and control the introspection periodicity. And finally, to reiterate, all the listed microservices can be deployed by the tenant itself. So the answer to the question we asked previously is yes, we can design a software introspection service which is non-intrusive, general purpose, and tenant controllable. Next, let us see a prototype implementation and workflow. Starting with an instance that is required to be introspected, which is provisioned using M2, that is malleable metal as a service. It is a diskless provisioning service. For the image management service, we use Ceph, which is a scalable high-performance distributed file system. The instances are provisioned over the network using iSCSI. We modified M2 with the features required for introspection and orchestration services. So when an introspection request arrives, a snapshot of the provision instances image is created. The snapshot is a read-only linked clone of the provision instance's disk image. The snapshot is then mounted as a standard file system for introspection. The introspection service then crawls through the mounted file system tree and generates frames corresponding to the operating system and software packages present on the mounted file system. It stores these frames to a JSON file. In our prototype implementation, we used IBM's open source agentless system crawler to create the relevant introspectable state of the mounted system. Once the introspectable state is created, a vulnerability detector compares it against a pre-populated database of existing common vulnerabilities. A limitation of our system is that it can only introspect for vulnerabilities that can be detected via persistent state of an instance. This brings us to the evaluation of our prototype. Our analysis of real-world application demonstrates that our approach is lightweight and scalable and has a negligible impact on the performance of applications running on the instances being introspected. On the slide, you can see the experimental setup that was used during our evaluation. All the experiments were conducted on the Massachusetts Open Cloud. Note that we used two VM configurations for hosting the provisioning and the introspection service. This helps us in providing insights to tenants operating at different scales. The first result is the time to introspect a single instance for vulnerable software packages. As you can see, the time taken to introspect a single instance is less than 10 seconds for both the setups. Note that the time difference to introspect the instance with two setups is also not significant. This indicates that the introspecting of an instance for vulnerable software packages is a lightweight process. Next, we analyze the network traffic between the introspection service and the image management service, that is the SES cluster. As you can see, about 78 megabytes of total data was transmitted and received over a 10 gig network interface while processing a single introspection request. This provides us insights on horizontal scaling. Next, we analyze the time taken to process concurrent introspection requests. As you can see, the time to process concurrent requests increases as we increase the number of concurrent requests from 1 through 32. This difference in processing time indicates that our system design can clearly benefit from vertical scaling. In this experiment, we analyze the time taken to introspect an instance for different introspection techniques while running different applications. In the interest of time, we skip the details of different introspection techniques which can be found in our paper. As you can see, for every introspection technique, the variability in the introspection times is fairly low, which means for a given introspection mechanism, estimating its resource requirements is not difficult for different class of applications. Next, we studied the impact of periodic non-intrusive introspection on a single application when running with different compute intensities and on different applications. For both cases, the instance was introspected 3 times during the lifetime of each application at an interval of 1 minute. Introspection of each application started after bootstrap of the application and the application runtimes averaged around 3 minutes. It was observed that there was no visible degradation in the OLTP throughput due to introspection as the number of threads for MySQL was varied from 1 through 32. Similarly, with different application occupying the entire instance resources, there was negligible performance impact due to a non-intrusive introspection approach. So with these results at hand, we estimate that in order to introspect 10,000 instances, our approach would require only 23 servers with 32 CPUs, 64 gig RAM, and 10 gig NIC, compared to reserving 1200 server worth resources for agent-based approach. That brings us to the end of this talk. To conclude, let's summarize what we saw. In this work, we proposed a general purpose and tenant controllable approach for non-intrusive software introspection. Our approach assumes that cloud instances are provisioned to remote virtual disks. By introspecting the snapshot of these live disk images, we mitigate the issue of trusting a potentially compromised agent during vulnerability analysis. Our approach also eases the at-scale management of introspection through a centralized service. Furthermore, our prototype implementation demonstrates that the resources required for our proposed approach are modest and organizations can easily scale up or scale out as per their requirements. Before ending, I would like to acknowledge the Massachusetts Open Cloud Engineers, master's student from Northeastern University, Massachusetts Open Cloud Commercial Partners, and the National Science Foundation for their support. Thank you for listening to this talk. If you have questions, you can ask them on the IC2E Slack channel or send me a direct message.